So today's my talk is right and left in living organisms. The problem of right-left symmetry is very familiar issue. So as you can see, so this is a Chateau Chambord in France. It's very famous chateau, and this architecture has perfect right-left symmetry. And here is a garden of one of the garden of the Versailles in France. This garden has made up with right and left symmetry. But Japanese castle and Japanese garden have not right-left symmetry. And here is a flower arrangement. Here is a Western style. Western style likes a symmetry. And Japanese style likes a symmetry. So that these difference between culture of the difference of culture between Western style and Japanese style is very interesting. Right and left symmetry exists in nature. Here is a right-handed snail, and this one is left-handed snails. The population of right-handed spiral structure is greater than that of left-handed spiral. And here is an example of IV. So this one is right-handed spiral, and this one is left-handed spiral. The orientation of the spiral depends on the species of the IV. This one is DNA and protein. DNA and protein, alpha helix of protein, have right-handed structure only. The nature likes a one-handed structure. The protein is composed of amino acids, many amino acids. Amino acids has this structure. This is a structure of amino acids. Amino acids bound to the alpha carbon bond to carboxyl group and amino group and hydrogen and side chain. Side chain means 20 different types. So acidic, basic, and hydrophilic and hydrophobic structure properties. The properties of amino acids depend on the side chain properties. Amino acids has also right and left in molecules. This is very important. On the primitive Earth, so the chemical and physical properties exactly the same, L and D amino acid. L amino acid means left-handed structures, and D amino acids means right-handed structures. On the primitive Earth, so the left-handed and right-handed structures are exactly same amount. And so on the primitive Earth, amino acids combined to each other and to make a short peptides, like L-only peptides, D and L mixtured peptides, and only D peptides. But during the evolution, D amino acid and eliminated, and D and L mixtures and D peptides were eliminated on the primitive Earth. And short L polypeptides evoked to the protein. Protein can get a folding structure and get a function and linked to the emergence of the life. So this is a one-handed structure. We are all one-handed structure, L amino acid polymers. So homochirality consists of L amino acids on Earth is essential for life. Therefore, nobody doubted the existence of D amino acids in the current protein. But D-aspartate is a kind of amino acids. D-aspartate increase in various proteins during aging. So, establishment of homochirality linked to normal life activity, that is evolution. If this idea is right, during aging, the loss of homochirality linked to the loss of function and onset of the diseases. This idea is paradigm shift in the life science, I think. And you can see, so which woman is elderly person immediately, because you can see the white hair and white eyes and wrinkled skin. But so that we cannot quantify in the amount of white hair or wrinkled skin. So these phenomena is not useful as a molecular index of aging. But so in the D-aspartate were found in the protein from the brain, eye, and skin, and with other tissues. That is, so the proteins composed of L-amino acid, only L-amino acids in young women, but in the elderly women, so the D-amino acid containing proteins were found in eyelids, skin, and brain, the other tissues. And so the D-amino acid is increased with age. That is, D-aspartate, the amount of D-aspartate is expressed as a function of the time. So that is why D-Asp is a mirror of life as a molecular index of aging. This table shows the D-aspartate containing proteins in various aged tissues in the living body. For example, in lens, alpha-A-crystalline has high amount of D-aspartic acid at various sites. These are related to the age-related cataract. In the brain, beta-amyloid protein, myelin protein, histone H2B protein contain Asp residues with high amounts and related to Alzheimer's disease, multiple sclerosis. This is one of the age-related diseases. In aorta, elastin protein has also contained the D-aspartic acid. It is related to the atherosclerosis. In skin, elastin, keratin, collagen has D-aspartic acid related to the solar elastosis. We focused on the D-aspartic acid in crystalline proteins and cataract. What is a cataract? Cataract are very common in elderly people. By age 80, more than 90% of people develop cataracts. A cataract is clouding of the lens in the eye that affects vision. If the lens is cloudy from a cataract, the image you see will be blurred. So what causes the clouding of the lens? We think one of the causes is maybe the D-Asp formation in the lens proteins. This is the eyeball. Lens is located here. The role of lens is to provide the transmission of the light to the retina for proper vision. Lens component is very simple. 65% of water and 32% of alpha, beta, gamma crystallines. Alpha crystalline is a huge aggregate composed of alpha A subunit and alpha B subunit with molecular mass 20,000 Dalton. And alpha crystalline, it interacts with the other crystallines, beta and gamma crystalline, to each other to make stable aggregates and to keep transparency of lens. But during the aging, D-aspartate generated in these crystallines, abnormal aggregation of proteins generated. This one is linked to cataract. So, how does an ASP residue invert TD form in a protein spontaneously? Here is a mechanism of isomerization of aspartic residues in a protein. Normally, so the L amino acid to D amino acid, inversion of L amino acid to D amino acid is very difficult under the physiological conditions. But in the case of aspartic acid is very easy to deform because here is normal L-alpha aspartic acid. Nitrogen, when the nitrogen of next amino acids attacks to this carbonyl group, L-succinimide is by intramolecular cyclization. L-succinimide is generated by intramolecular cyclization. This L-succinimide is very unstable, and to L-succinimide to invert to D-succinimide through this intermediate. D-succinimide hydrolyzed to D-beta aspartyl acids and D-alpha aspartic acid residues. Similarly, L-succinimide hydrolyzed to L-beta and L-alpha aspartic acid. So, there are 4 different isomers spontaneously generated in a protein. And this reaction occurs when the next amino acid is small, such as glycine, serine, and alanine, because the succinimide is easily formed. So, what happens to the protein structure by the appearance of D-beta-Asp residues? Here is a normal L-alpha aspartyl residues. This is abnormal D-beta aspartic acids. Deformation would induce opposite orientation. This one is here, and another one is behind of this area. And so the side chain of Asp residue is opposite. And this one is normal L-alpha aspartic acid. The number of bonds, the next C-alpha of amino acid, the number of bond is 1, 2, 3, 4. 1, 2, 3. But so in the case of D-beta aspartyl residues, 1, 2, 3, 4. So that is a problem. Beta linkage would induce longer of the length of peptide backbone. These isomers affect on the structure of protein and induce abnormal aggregation. Therefore, it is very important to seek the hot spots of these isomers in protein. So how to detect the specific Asp isomeric sites in the proteins? It is very difficult to identify the hot spots of Asp isomers. Identification of very small quantity of D amino acids at specific sites in the protein comprised almost entirely of L amino acids is like looking for needle in the haystack. The previous analysis of isomeric sites was very complicated and time-consuming. Now we recently developed a new, precise, and quick analytical method for the individual isomers in a protein from age-related diseases. Here is an example of lens. Lens were homogenized and separated into water-insoluble protein and water-soluble protein by centrifugation. Water-soluble protein contains normal crystalline proteins, and water-insoluble protein contains abnormal aggregates. These proteins were digested with trypsin 37 at 37 centigrade for 20 hours. The resulting tryptic peptides applied on LC-MS. So that we can identify the tryptic peptides and determine the amounts of these isomers at individual ASP residues in all crystallines. Here is a LC mass chromatogram of the tryptic peptides of crystalline from an elderly donor. We can identify the tryptic peptides by MS-MS analysis. MS analysis give us the amino acid sequence information. That is, we can identify of the peptides. And how to identify the isomeric peptides with the same mass? Generally, each peptide is eluted as one peak with one mass number on LC. But we found the one peptide is separated on the LC mass, so as multiple peaks. For example, alpha A 55 to 65. This peptide is all sequence is the same. TVL means threonine, valine, leucine, aspartic acid, serine, glycine, isoleucine, serine, glutaminyl acid, and valine and arginine. So that these peptides are the same mass, but has multiple peaks on the LC because this one is 4 isomers, L-alpha, L-beta, D-alpha, D-beta at ASP58. That's why the same sequence peaks were separated on the LC. So that is ASP isomer containing peptides. MS-MS is the same and multiple peaks. There are multiple peaks on LC. That is ASP isomer containing peptides. We can distinguish these isomeric containing peptides. These isomeric containing peptides very easy. So now next step, which peaks corresponded to these isomers. So we synthesize the standard of peptides, these peptides as standard peptides by matching with the elution time. So the first one is L-beta ASP containing peptides. The second one is normal L-alpha ASP containing peptides. Third one is D-beta ASP containing peptides. And last one is D-alpha containing peptides. We can identify perfect. So now we can show the hotspot ASP isomers in aged human alpha crystalline. ASP 58, 76, 84, and 151 is hotspot in human alpha crystalline. Human alpha crystalline has 173 amino acids, but only 4 aspartic acid sites are specifically isomerized. ASP 58 and 151 residues are located in flexible N-terminal and C-terminal region. And the neighboring amino acids of ASP58 and 151 are serine and alanine. That's why these residues easily susceptibility to the L and L convert to D amino acids. So here is a hotspot of isomers in aged human alpha-B crystalline. Aged human alpha-B crystalline, ASP36 and ASP62, only two aspartic acids is specifically hotspots. And ASP36 and ASP62 residues are located in flexible N-terminal region. This makes sense. And so this is a summary of the relative amounts of ASP isomer at various sites from alpha A and alpha B crystalline from water insoluble. Water insoluble means this abnormal aggregated. And double-S water-soluble fractions of lenses elderly donors. ASP58 and 151 and ASP62 of alpha-B crystalline show a high degree isomerization. As you can see, the blue one is normal L-alpha, red one is abnormal L-beta, green one is abnormal D-alpha, purple one is D-beta. And so the amount of normal L-alpha aspartic acid residues is lower in water insoluble fraction at all ASP sites. And among these abnormal isomers, D-beta aspartic acid isomers in dominant. Here is a relative amount of ASP isomers at position of beta amyloid protein of Alzheimer's diseases. In this case, among the isomers, abnormal isomers, L-beta is predominant. But in the case of crystalline, the D-beta aspartic acid, maybe so the surrounding of the structure of the ASP residues is different from the crystalline, between crystalline and A-beta ASP protein. This is a summary. Proteins are composed of exclusively of amino acids. However, the amino acids generate during aging. The appearance of the amino acids alter the protein assembly and structure and function. The mechanism underlying the onset of age-related diseases may be solved by considering the presence of the amino acids in L-amino acid world of life. Today's topics limited protein-bound D amino acids, cataract, Alzheimer's disease, age-related macular degeneration, and so on. But in our living body, there are free D-serine, free D-alanine, free D-aspartic acids in our living body. So free D-serine functions as endogenous synaptic modulator, and free D-alanine has osmolyte function. And free D-aspartic acids are novel messenger in the maturation and differentiation of tissues. And the amino acid containing short peptides are opioid peptides. Thank you very much for your attention.